today I'll be talking about the solid principles. My name is Harlan Kellaway. I'm an iOS engineer here at Prolific Interactive. And so what is solid? Solid itself is actually an acronym, SOLID. It stands for 5 basic principles that, when applied together, are supposed to make it more likely that a programmer will create code that is easy to maintain and extend over time. So what it actually stands for is single responsibility principle, open close principle, Liskov substitution principle, interface segregation principle, and dependency inversion principle. I find a lot of engineers are familiar with some of these, maybe even all of these. Maybe they don't have the words for them. Most often, single responsibility principle rings a bell with folks. What Solid provides us with is increased code confidence in the fact that when we extend, modify, refactor code, that it will be doing what we think it's doing. It also helps facilitate a common language. We can start saying stuff like, hey, I think this class is violating the single responsibility principle, and other engineers understand what we mean. It also helps us think about the areas of our code that change often, and the fact that we should be trying to encapsulate the areas of our code that change a lot. And while we're not going to be talking about testing today, it actually makes your code easier to test, which is always a good thing. So first I'm going to talk about what each of these principles are, and then we're going to go into some code samples. So we'll start with S. This is the single responsibility principle. This is the one that engineers sort of get, which is that each class should have a single responsibility. And responsibility is defined as a reason to change. Now, I say most engineers get this, but I think we could all do a little more to think more critically about the fact whether our classes actually are violating this principle. I think I've done this myself where I create a class, I think it has one responsibility, and really it's doing 2 or 3 things. So SRP tips. Every entity you create, you should be asking yourself, what is the one thing that this thing does? And if you have to use the word and to describe what your entity does, you're likely violating the single responsibility principle, and you should think about breaking your class down into various objects. So the open-close principle. This one is a little harder to grasp. It says that software entities should be open for extension, but closed for modification. The idea being we shouldn't have to be opening up the internals of our class. Once they're written and they have their expected behavior, if we're opening up the internals to add to that expected behavior, something is wrong. We're going to see an example of this later that I think will help clarify what that actually means. So OCP tips. If you have to modify a class each time you add expected behavior, you should revisit this principle. A good tip-off, a clue might be if you have these giant, sometimes if-else or switch statements where you have to open up the class and add a new case to the if-else or the switch statement to add to the expected behavior of the class. Sometimes that's a clue that you're violating OCP. The Liskov substitution principle is an interesting one. It actually deals with inheritance, kind of a taboo topic sometimes in clean coding circles, but when you deal with inheritance, it says that objects should be replaceable with instances of their subtypes or subclasses without altering the correctness of the program. And again, we'll see an example that I think will help clarify what that means. But LSP tips, subclasses should not break expectations of their parents. If you were to swap out 2 subtypes, they should not alter how the program actually runs. And another implication is that you shouldn't have to know the actual type of a subclass to know what's expected. So if you have animal superclass, cat, dog subclass, your client code shouldn't have to be like, is this animal a cat, then do this. Is this animal a dog, then do that. If you're doing that, it's likely you're violating the Liskov substitution principle. So I is for interface segregation principle. It tells us that many client-specific interfaces are better than one general-purpose interface. So this is often represented when you have a protocol interface that is large. It doesn't actually have to be large, but various clients use the same protocol, and you're exposing some of these clients to functions that they shouldn't be able to call, and that's dangerous. So ISP tips. So when you do have monolithic interfaces, you might be violating ISP, and maybe it's time to break it down. Or when you have a lot of different objects that use the same object that is behind a protocol, you might be violating ISP. And really the point of all this is to keep consumers, clients from having too much power, from being able to call or modify state that they shouldn't be able to modify. And we'll look at an example of that. And lastly is the dependency inversion principle, perhaps the hardest one to grasp. It says that high-level modules should not depend concretely on low-level modules. They should depend on abstractions. Dependency inversion often leads into talking about dependency injection, and these in and of themselves could probably be their own talk. It's a big topic and a worthwhile topic, so we'll only touch on this a bit. But let's look at this. We are used to writing these higher level classes that use a bunch of low level classes concretely to get what they're to orchestrate what they need to do. DIP teaches us that these higher level classes should actually be creating interfaces, protocols of what they expect to be done. They need to describe what they need to get done, and then the lower level objects fulfill these, and it's your system's job to sort of hook up what lower level objects the higher level objects are using, but the higher level object doesn't need to know the details of the lower level objects it's using to get done when it needs to be done. So if you look at this graph, on the left here, the policy layer is our high level entity. It uses various concrete objects from the mechanism layer to get what it's done when it needs to get done. And then the mechanism layer uses lower level utility stuff concretely to get what it needs to get done. What we should strive for, rather, is the policy layer describes via protocol, this is what I need to get done. Mechanism layer has various objects that fulfill that, and so on and so forth. So we'll see a bit of that too. So that was a high-level description of those 5 principles. Now we're going to look at some code to actually see these principles in action. Before I do that, I want to mention that the example and some of these code and ideas and conclusions are actually taken from an iOS Soho talk on the solid principles done by Danny Hertz from Uber. So thank you, Danny Hertz. So the first example that we're going to be looking at is one that says we have a partner. They're making a real-time Twitter client that automatically updates the timeline and the profile of users at certain frequencies. So specifically, we're going to have a timeline service that updates every 1 second, and we're going to have a profile service that updates every 2 seconds. So let's first look at how we might implement that, a very reasonable way to implement it, and then look at how it actually violates solid principles. So we're going to switch over to Xcode now. Cool. So our first stab at this would look something like this. We have a timeline service here. Our timeline service does not actually update anything in this example. It simply prints to the console. Fetch timeline for user. We have a profile service that does a very similar thing. Fetch profile for user. And then we have sort of the heart of this example, which is something we call our scheduler. Our scheduler responsibility is to, the client can tell the scheduler to start services or stop services, and its responsibility is to make sure these services go off at the expected frequencies. So, service scheduler. Let's take a look at how we would start actually building this thing. In this implementation, since we're using timing every 1 and 2 seconds, we decided that we're going to use internally an NS timer. We're also going to keep track of the tick of the timer because we're going to need to do things on every 1 and every 2 seconds. So the heart of our scheduler is the fact that we can start the scheduler and stop the scheduler. When we start it, the services start going off at the expected frequencies. So start, in this case, would look something like this. We simply create our NS timer instance. We tell it it's going to go off at every 1 second, and we have a selector it's going to call that's called timer did fire. Stop, as expected, would be just stopping that timer, invalidating the NS timer, setting it to nil, and resetting our timer tick. And then really the meat of this is our timer did fire function. So this is called every second by the NS timer. On timer did fire, we increment the tick that we're using, and we call run services with the value of the new tick. Run services says if the tick is a multiple of 1, i.e. every 1 second, run the timeline service. If the tick is a multiple of 2, i.e. every 2 seconds, run the profile service. And then running the timeline service looks like this. We call fetch timeline for user ID on timeline service, and we call fetch profile for user ID on profile service. So this is sort of a very reasonable implementation here, and it actually works as expected. It works quite well. So here in our client, we create a new scheduler and we tell it to start. And what we'd expect to see is that every 1 second and every 2 seconds, we actually print to the console. So as expected, we can see down here that every 1 second, timeline service is going off. Every 2 seconds, profile service is going off. Our implementation works, but what solid tells us is that not that the way you're coding doesn't work, but that there are better ways to do what you need to get done. So let's look at a more solid implementation. But first, let's evaluate what went wrong. So we actually have, in this very reasonable implementation, several violations of solid. We have a single responsibility principle violation, we have an open-close principle violation, and we have a dependency inversion principle violation. And we're not going to talk about testing, but I guarantee you this would be very hard to test. So the SRP violation actually comes in the fact that this scheduler object has a lot going on. It knows how to do a lot of things. First of all, it uses this NS timer. It manages this NS timer. It knows the intricacies of the NS timer. It knows how to schedule the services. Second is that it now manages the knowledge of the frequencies of when actual services go off. It knows that timeline service goes off every 1 second. Profile service goes off every 2 seconds. So it has that responsibility. And it also has the responsibility of knowing precisely what the service implementations are and how to incite them. So it knows we have a timeline service, and it knows we have a profile service, and very concretely, we need to call fetch timeline and fetch profile. So this is too many things for one thing to do. We also have an OCP fail, DIP fail. If we ask ourselves, how would we actually add a third service to the system? What would we have to do? We'd actually have to go back to our run services with tick function and add another if statement. If we wanted to change the frequency of service execution, let's say we wanted to make timeline service go off every 3 seconds, again, we'd have to open up scheduler and change this value from 1 to 2. So DIP failing comes here in this fact that, again, scheduler has these very concrete dependencies. It knows the intricacies of timer, it knows the intricacies of frequency and services. If we needed to change how the profile service actually worked or how the timeline service actually worked, very simply, if we changed the function signature for fetch timeline, we'd have to also open up scheduler. And we're starting to see in that very small example a sort of cascading of dependencies. We have to change timeline service, so we have to change scheduler. And this is what is called tight coupling, and it's something we should avoid. So let's look at a solid example. The first step often I find in breaking things down in accordance to the single responsibility principle is by recognizing what each of the players are. So in our case, we had really 3 players. We have services, we have a timer, and we have a service scheduler. So I often then go ahead and create protocols for those separate entities that I'm dealing with. So for a solid example, service would look something like this. Services can be executed. The client, in our case a scheduler, doesn't need to know how it's executed. All it needs to know is that it can execute a service. And we're also tying into service the frequency property, because that's really more related to the service than the service scheduler. A service can now say, this is how often I need to be run, and the service scheduler can be dumb. It can just run it on its frequency. Timer is another entity we're using. In our instance, all we really need to do with our timer is be able to start it, be able to stop it, and be able to associate an action that happens on every tick with it. So our timer has this interface. And then service scheduler itself has this interface. We need to be able to start it, and we need to be able to stop it. So let's take a look at services, timer, and scheduler in this example. So our timeline service looks something like this. And remember, all it needs to be able to do is say its own frequency and say how it's executed. So if we look at the execute function for the timeline service, it's exactly the same as before. It's just printing out to the console, but now that knowledge is within this object, solid timeline service object. Additionally, it returns its own frequency, which we know is 1. In our implementation here, we actually provide that frequency in the initializer. Why we don't have to actually concretely tie the 1 to timeline service. We can introduce it when it's initialized. Profile service looks very much the same. Its execution prints to the console. Timer, we have a solid timer object now that adheres to the timer protocol, which has start, stop, and on tick. Now, we've decided that our timer is actually going to use an NS timer internally, but we have the implication here that we could have actually implemented this in another way and swapped out a different concrete implementation. But in this case, we're using NS timer internally. When we set it up, we create, when we hit start or when we call start, we're doing very much the same thing. We're creating the NS timer. We're saying timer did fire is the function that's going to call every second. Stop is also the same. And the addition that we've added here is that we now have an on tick action. The client, in this case the scheduler, can associate an action that happens on tick. And timer did fire looks very similar, but it's a little more abstract. It increments the tick, and it calls whatever tick action is associated with it. It doesn't need to know what the tick action is. It calls that tick action, if it has one, on every tick. So now our scheduler actually becomes a lot simpler and a lot more abstract. So if we take a look at scheduler, what we need to create a new scheduler is that it needs to be given a timer. But it's important to notice that that dependency right there is abstract. It is not concrete. It no longer needs to know that it's an NS timer working behind the scenes. All it needs to know is that it has a timer to work with. And a big difference in this implementation is that we have an array of services. And again, service is abstract. We don't know that there's a timeline service. We don't know that there's a profile service. We don't know if we have 70 services or 1 service. It doesn't matter to the service scheduler. All it needs to know is that it needs to execute these services at certain frequencies. So we have this array that we're maintaining of services. And the big difference comes here in that we have this new function called register service that adds a new service to the scheduler, any number of services. Its internals aren't tied up in the fact that there's a timeline service and there's a profile service. So now, starting this service, what does that look like? Calling start on the scheduler, rather. So when we call start on the scheduler, it tells its timer, here's the onTick function that I need you to use. OnTick, we're going to call my own timer did tick function, and you can go ahead and start. And stop, as probably expected, all it does is it tells its timer to stop. It doesn't have all of that stuff about NS timer being invalidated. And really the heart, again, of the scheduler is its timer did fire function, which we can see is very similar in certain ways. So its timer did tick function calls, again, run services with tick. But if we look at run services with tick, it's a lot more descriptive of what's going on. It's not about, I need to check every 1 second and every 2 seconds and its timeline and its profile. It's for every service I have, if I should execute it for its frequency, then execute it. It actually reads more like a sentence or two than the concrete details of what's going on. So beautiful. If we're to actually look at how this is run, again, it's very similar to what we were doing before, which is we need to create a new scheduler object, and then we need to tell it to start. And what we'd expect to see is that, as before, the timeline service is called every 1 second, and the profile service is called every 2 seconds. And we can see that right here in the console that's going on. So both worked exactly the same way. They both worked. But one sort of broke things down a lot more, a lot clearer. And we have a win here. We can now say that scheduler, service, timer all have one and only one responsibility. We also don't have to open up scheduler every time we're changing services or frequencies. It sort of has its own responsibility, which is no matter how many services I have, I will run them at the correct frequency, but we don't need to open up its internals every time we need to add a new service or change a frequency. Additionally, the dependencies that it has, which in this case is timer and also a set of services, are abstract. And if we had to write tests for each of these individual things, for the services, for the timer, for the scheduler, it would be a whole lot easier. Okay, so that was a lot, but you might be asking yourself a couple questions, which is, one, okay, you made this class called solid timer that adheres to timer, but how did scheduler actually know that it was using an instance of solid timer? How did that happen? And how does it know that timeline service and profile service are the services that it's using? And what about the fact that you actually tripled the amount of files that you had there for that second example? And then you really only talked about 3 out of 5 principles. So I'm going to answer those first 2 questions, and then we're going to see much shorter examples of the Liskov substitution principle and the interface segregation principle. So about the concrete instances that scheduler in our second example was using, to answer that question, we're actually veering away from the solid principles. This isn't a matter of solid. This is a matter of your own application, your own system, and how you handle dependencies. So that's when we start veering to the dependency injection talk. So we won't go much into there. But I'd like to demonstrate the solution that Danny Hurt suggested that I also happen to use, which is the idea of using factories to actually encapsulate object creation. So what we actually ended up doing in the second example there to introduce dependencies was we have these factory objects. If we take a look at the factory for service scheduler, we can see that we have a function on it called service scheduler with ID, and it provides us, its return type is actually an abstract service scheduler. Again, it doesn't need to be concrete. We decided that we're going to use a solid service scheduler. That's our concrete instance. And solid service scheduler needs a timer. Another factory function is used down here to introduce solid timer. But again, we could swap that out with a different concrete instance. And it's here where we're actually registering various services with the scheduler that we're intending to use. So we register a timeline service and we register a profile service from actually another factory. And it's over here in the service factory that we introduce the fact that timeline service is running every 1 second and profile service is running every 2 seconds. So what we ultimately achieve with this is, one, we're starting to think of object creation as its own responsibility, which is a great thought to explore. And 2, we're sort of making these things that were tied up in the internals of the scheduler before more like configuration values. Yeah, the frequency is 1 and yeah, the frequency is 2. But if we needed to change those things, we shouldn't actually have to change the way the application works. These are just values. So that's really food for thought. That's not a solid topic. But that's the way I've been tending to do things more and more. So what about the fact that we tripled the file count in our second example from the first? Do you think it's a bad thing? So this is more of a debate question than there's a clear answer on this one. I would say that in the second example, our objects were so much cleaner, so much smaller, so much easier to comprehend that we actually gained a lot of value over the first example. That's very clear in a very small example, but as applications grow and grow and grow, you can get into hundreds and hundreds of thousands of files, and that's where it actually becomes hard, especially hard for the engineer that comes after you and doesn't know how you think. So that, to me, is more of a organizational issue, how you manage your code base, how you onboard people, how you document things, than we should sort of throw these principles away because they necessarily result in a larger amount of files. So again, that's food for thought. Naturally, trying to follow solid will lead to more files, but smaller files, easier to comprehend and easier to test. Okay, so let's talk about the last 2 principles. This is the Liskov substitution principle and the interface segregation principle. To revisit what Liskov says, it's that objects should be replaceable with instances of their subtypes. So back to that animal, cat, dog example. If our application, our client code is using an animal, we should be able to use a cat or a dog concretely without changing how the application runs. So the classic example of Liskov uses a square and a rectangle with the idea that, a square is a rectangle. That's true in geometry. So why not model them that way in your application? Maybe you can see the issue. let's take a look. So in this example, our rectangle, in a not solid example, our rectangle looks like this. It has a height, it has a width. We can set the height and we can set the width. And then what our client really wants to get from this is the area of the rectangle. Square. How do we achieve the fact that the invariant that the height and the width need to be equal when we have a square as opposed to a rectangle? We've decided that we're going to override the set height and the set width functions and set both values to that new value. So when I set the height, I'm also setting the width to that value. When I set the width, I'm also setting the height to that value. This may seem like, okay, simple enough, but it actually very quickly gets to having an issue, which we can see here. So in this example, I'm making a rectangle. I'm setting the width to 3. I'm setting the height to 7. I then make a square. I'm setting the width to 3, and then I'm setting the height to 7. And in the rectangle, the area comes out to be 21. And with the square, the area comes out to be 49. You might be like, yeah, of course. But the issue is that, let's imagine we had a client that was using a rectangle, and they've written their client code. It works as expected. They call area, and area should be 21. The next programmer comes along and replaces rectangle with square. You can do that because square is a rectangle. But now, lo and behold, area is 49. We've violated what is expected of the class that we're using. So the way to actually amend this is to recognize that we can't model square as a rectangle because it's a violation of the Liskov substitution principle. Another way we could solve this issue is if we recognize that both of these have a relationship in the fact that they're shapes, and a shape has an area. That's really what our client code wants. So in this example, rectangle will have a width and a height, and its area will return width times height, and it's a shape. Square, also a shape, no longer a rectangle, but a shape. It only has a side, and its area is side times 2. So if we were to imagine that in our client code, we were actually just using a shape object, or rather, we would be forced to use either a square or a rectangle and call area on it. Or maybe all our client really needs to do is work with a set of shapes and call area on it. So here we see we create a rectangle, width and height of 7, the area is 21, and a square, side of 3, as expected, the area is 6. No longer an issue. Cool. So the last principle is the interface segregation principle. And in the classic example with this one is an ATM. So remember, the interface segregation principle says that client-specific, a bunch of client-specific interfaces are better than one general purpose interface. So if we look at this diagram here, our general purpose interface in this example is the ATM UI interface. It has request deposit, request withdrawal, request transfer, inform insufficient funds. Now we need this interface because there are actually several concrete implementations of it: speech UI, braille UI, screen UI. But if we look over here at the way we're actually using this this interface, it's used by various transaction type objects that can be executed. So there's a deposit transaction, there's a withdrawal transaction, there's a transfer transaction. Each of these transactions is given an object that adheres to ATM UI, and it calls the respective function on that object. So deposit transaction will call request deposit amount. Withdrawal transaction will call withdrawal amount. But we see here that because we're being handed ATM UI to deposit transaction, it actually has the opportunity to call something outside of deposit amount. It has the opportunity to call withdrawal amount, and that introduces the opportunity for error. So what the interface segregation principle would tell us is that rather, let's break down ATM UI into smaller interfaces that are client-specific. In this case, transactions are the clients. We can have a deposit UI that just has request deposit. We can have withdrawal UI that just has withdrawal and insufficient funds, and a transfer UI that just has request transfer. We have each of these transactions relying only on an object that adheres to those UIs, which concretely will be whatever adheres to ATM UI. But all deposit transaction needs to know is that it can call request deposit amount. So let's look at that in practice. Let's check out our ATM. So our not solid example, again, will have all these 4 functions. And we have this console ATM that adheres to solid ATM protocol. All it does is print to the console. Great. The issue arises here actually in the transaction object. It is given an abstract dependency, great, of ATM, something that adheres to the ATM protocol, and now has the opportunity to actually call unexpected things. So really, the deposit transaction should only be calling request deposit amount, but because it's exposed, it actually is able to call withdrawal amount, and you would not expect a deposit transaction to also do a withdrawal. That would be an issue. So what the interface segregation principle would tell us is that our ATM protocol can actually adhere to a bunch of smaller client-specific protocols. So in this case, deposit UI only has request deposit amount, transfer UI only has request transfer, and withdrawal UI only has these 2. Our console ATM can still adhere to ATM protocol and still do what it needs to do. But on the other side, our deposit transaction is now only given a deposit UI object and can now only call request deposit amount on that object. Cool. So to wrap it all up, when you're coding, you should be thinking about the solid principles. You should be thinking about whether your fellow engineers are perhaps violating principles. And you can ask yourself various questions. This entity I just created, how many responsibilities does it have? If I'm using AND, I'm likely violating the SRP, the single responsibility principle. Do I find myself constantly opening up this class that I've already written? It already has its sort of behavior set when I'm adding to its expected behavior? Are these subclasses I have genuinely substitutable for each other without harming the client code? Is this client actually exposed to functionality that it shouldn't have? Am I literally able to call functions I should not have access to from this class? And in a broader way, what parts of my classes are changing a lot? And how can I use these principles to help encapsulate what changes a lot and make sure I'm not violating that? Do my classes depend on concrete dependencies? You cannot always get away from the fact that you depend on concrete dependencies, but you can move towards depending on abstract dependencies probably a lot more. And if you're still using Objective-C, does my class need this many imports? If you have a whole ton of imports, we've all written code like this, we've all seen code like this, this might be a clue that you're violating any or all of these principles. And if you want to find out more about this topic, I highly recommend Practically Solid by Danny Hertz. That's where I got the first example, and some of these points from the Wikipedia article on Solid is actually very good. There's a tutorial out there by Toots Plus on it that's very good. And there's videos by a Ruby developer named Sandy Metz. She talks a lot about this, and it's good stuff. So, thank you.